what is a neural process? It's a distribution of a function, same as Gaussian processes. That's the thing that we're going to stress out a lot, is the Gaussian processes is not a single function, it's a distribution of multiple functions. And therefore, neural processes inherits that and becomes a distribution of the functions. Another thing, it rapidly adapts to new observations. And that's important. This is a benefit from Gaussian processes. When you have a neural network, when you train a neural network, you can't really tune it after that. I mean, there's multiple other like the nuances, but in general, you train a neural network, you got your weights, that's it. The model is a black box. From there, you can just do the predictions. And it's much harder if you have to add additional observation to it to make sure your model gets this new learning. Like they have variations like meta learning and incremental learning, which tries to address that with tuning your weights from a neural network, so you can take into account what you haven't seen before. But with the neural processes, now that becomes automatic, so which is a big plus. Another big plus, which also comes from Gaussian processes, is now that you can model uncertainty. So people say like, well, why do you care about uncertainty? For some reason, people do. Every time that at work we have any kind of project that we are working on, everybody's asking us like, how confident you are that you are about your results. And then so this confidence comes in as the questions all the time. No matter what you're doing entity extraction, or you're doing the prediction in time series, or you're doing the recommendations. They always ask this question: give me the confidence. And uncertainty lies excellent in that for people to be able to say something about the confidence of your models, your estimations. So all of these three things, the distribution of the functions, new observations, and uncertainty, come from the Gaussian processes. And what comes from a neural networks is that they're very, very computationally efficient. So that's their combination. That's why you have four different aspects of neural networks. So far, so good. Okay, so if so far so good, we're gonna get into the weeds of why I love the paper. So here's the where things started clicking for me. So on the left, I have a graphical model. This is a standard notation for graphical models. And then what does these circles and arrows and rectangles and colors mean? So the gray circles means that you have observed the data. So the YC and XC, these are your context, your observations. It's like, so essentially it's going to be your training data and your labels. The gray circles, the observations. Z is a hidden layer. That's your latent space. So your information flows from the training data to a latent space. That means that there's in the graphical world, you would say the information flows from Y to Z. In a neural network perspective, you would say that the Z is embedding, is a mapping embedding between the training and latent space. So that's that. And then Z is not colored because it's not observed. It's hidden from you. Now the next square is where you have XT and YT. That's target. So that means that you observe new examples, new instances, and you have to predict what the Y is. It's like testing. You have the training set and you have a testing set. So this is how generally the graphical models will be represented. And the big squares means that it's a stacked model. So you can add as many of these pairs as possible. That means your example. So you're adding one example, second example, third example, fourth example, so on and so forth. And then instead of putting like X1, Y1, X2, Y2, and then so on and so forth, it's much better just put them in a rectangle. It means that that's being repeated as a block. So that's the graphical model that essentially people who in this field would be very, very used to this notation. That's very clear, and it makes sense to me how the whole information works. That you map Z from the X and Y, and then you make and then as you're receiving the new axis, you make a prediction from a YT, and a YT drives from that Z. So here's a beautiful thing. So people who are now familiar with neural networks, the autoencoders. Sorry, somebody asked a question.
What's the difference between the gray circles and white circles?
The gray circles is the observations that you have seen it,
okay.
And the white circles you haven't seen it. It's hidden.
Got it.
It's like if you are thinking about standard traditional machine learning algorithms, you have a training data, and then your model is the sort of like latent state. You don't know the model. You learn the model from your observations, and then when you start predicting, you again see your examples, but you don't see the labels. That's why in the second rectangle, you're going to have the YT is going to be white because you haven't observed it, but you see the XTs.
Got it. Thank you.
Okay, so now the autoencoder. So with autoencoder, like it's almost like shifting the graphical model into the making it vertical and then seeing exactly the same way. You have the axis. So with X, you don't have the Y, so you don't need a label. So you only have the X, but it doesn't matter. Like you can combine X and Y into one variable, it's the same thing. So you have the X, and then information flows into the Z. Like that's the Z is like is like what you call bottleneck in the encoder, but it's the same thing as a Z in in the graphical models when you flow from the axis to Z, and then it's like this axis here is your color circles, and then X on the other side is also colored circles, but there's a XC and XT. So the context is what you have seen, and the target is where you want to go. And if you now kind of flip the autoencoder, like fold it in half, you're going to have exactly the same picture as you have in the graphical models. That's exactly the same thing. You have the X's here, you have X context here, X target there, and then a Z, if you pull it up, that's your hidden variable. It's exactly the same architecture. It's just that's what if you wanna understand further what neural processes are, this is where you kind of go from. You have the basic model or graphical model. You look at what an autoencoder is, and then we can move from there. Is there a question in chat?
Yes, there is a question. The question is, what is the difference between C and T? And is C equal to context, the training data, and is T equal to the target?
Yes, the C is the context, and then so for in the traditional traditional machine learning algorithms, that's going to be a training data, and then T is going to be your test data. But in this case, it's considered target. It's the same thing. It's just that what is the more common way of calling of naming these variables? Just consider context training and target your test.
I have a further question regarding the graphical model. I'm wondering right now, kind of like, is that a confounder or what would you, or an unobserved variable, and do you assume a sort of a causal structure there, and how is the directed acyclic graph, the causal structure, flowing in this graphical model?
So yes, there's a causality in here. So that means that the y and xc, they cause z. So if I bring an example, like let's say generally when we think about graphical models, we think about like we have two random variables, and these two random variables could be umbrella and a person, and then you observe both umbrella and the person, and then if you observe both of them, that causes and then you want to say cause in here the kind of information flow that you're gonna assume that there's a rain outside.
Yes. Okay.
Yeah, although the rain, it's that having an umbrella and then seeing a person does not cause the rain, but the information flow goes there.
Yes, I see now. Yeah.
And then the same structure still holds even if you don't have a causality. So if you remove the arrows, that just becomes undirected graphical models. And in undirected graphical models, their mathematics is somewhat similar. All you're doing is just adding the additional arrow in a different direction.
Okay. Yeah.
And then you asked something about a cyclical.
No, I was just wondering, but you kind of answered the question, because in graphical models, you kind of assume a directed acyclic graph. For example, you can do that in IV regression, so instrumental variable regression in econometrics, or also I guess nowadays biometry, where you can do Mendelian randomization. And there you have basically like this causes that and so on, and then you do a bunch of regressions and put one regression basically into to another, called two-stage least squares. And this is my understanding of the whole graphical models. I think they have something to do with that. But I need to check on that. I need to read Wikipedia on that.
Yeah. Well, yeah, the two different variations of graphical models in this case is going to be the directed and undirected. And undirected, they are the Markov random fields. Okay. And then it's again they're similar. There's a little bit trickery with how the inference works. Surprisingly, it's simpler to have that direction in your graphical models, because not having a direction just makes things a little bit more complex. Yeah, definitely. Yeah. Okay. So, but is that kind of clear to people that there's a analogy between the graphical models, and then there's an analogy between encoder architecture? It's an analogy in their architectures, not in the, there's a really like huge nuance in there, what makes them very, very different. There's Z here, Z on the, in the encoders, and Z here are very different concepts. Whereas Z in graphical models, that's a random variable. And the random variable means that you can sample from that variable to get any instance of your like if that Z is a normal distribution and you sample from there, you know the mean and the variance, so you're gonna get a number somewhere which belongs in your Gaussian distribution, in normal distribution. Whereas Z in the autoencoder doesn't have the parameters. It's just a mapping. It's like large vector. It's a vector which is a shrunken size from your input, because that's how we go. We go from, if you look at the image, we start with the size, 100 by 100. Your Z is going to be the decreased dimension of that. So it's going to be like the embedding of it, small embedding of that, like encoded version. But it's not a random variable. You can't sample from that.
It's like going from a prior distribution in likelihoods to a posterior distribution for Z, whereas the other one is like going from your distributions going to an expectation.
I like that statement, but essentially the other one is going to be, expectation is going to be in the autoencoder, because you've sampled it and then it's almost like that's it. You can't resample it more. It's a constant. That's all you get. It's deterministic. Versus the graphical model.
Yeah, that's what I was saying. The expectation is the autoencoder, and the graphical model is basically going from the Bayesian point of view here.
Yep.
Posterior.
Cool. So
one question on the previous slide. So what is the relation between that XT to YT, the arrow?
XT to YT, let me go back to the slide.
I think you touched upon that, but XT
yes, so the XT, that means that you observe now your new examples coming in, so you do see the record what X is, but you need to be able to label it. So that's your target. The target is that when you have you're trying to predict what we're trying to predict blah, 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 with labels. Maybe the height of the person. So if you're predicting the height of the person, the height, it would be your YT going to be at the target, and the XT is going to be the description of that person, like what are the features of the person. So the features might be like what's the gender, where they're coming from, like what's their weight, how old they are, all of that information. That's your X vector. And a Y is your scalar, is meaning that that's my my label. So when I'm trying to do the inference, in graphical models, we talk about inference, we don't talk about prediction as much. It's more like about you infer, you get that. And that's why the arrow goes that way, because from the XT, you observe the XT, and that leads to the YT, given that you have information about Z. So you learn the Y from the model you trained, and from the data that you observe. That's why it goes like that.
I see. Okay, thank you.
Alrighty. So here's the meat. That's how the neural processes looks like. Like in the paper they had this picture, and then we kind of broke it down, and we can essentially break it down a little bit further here. So that's your entire context. So if the big square on the left, so without even looking inside, that was our context. The whole thing is our Z, and the whole thing on the right is the target. So now Z is now it gets the information about what kind of Z, and then it gives the mean and the covariance coming to as a prior to the Z. So the bottleneck, that Z mapping in an autoencoder, got replaced with a random variable. So it's not just the plain old Z anymore. It's a Z beefed up with probability and a flavor to it, because now you can, like, it's not just it's not deterministic. You can sample from it, and there's information. It's like as soon as you put M and Z, and then that goes into the M, like mu and variance. That these are the parameters of normal distribution. And then how does that happen? So this is the kind of the important the important difference that I was kind of alluding to earlier. That's one. Second, what's really also very important is that now the context has to split into the multiple data sets in parallel. That's how you get not a single function, you get multiple functions. So instead of having just like one data set that you get, like whatever you get data sets like of 100,000 records, instead of training on all of it at the same time, what you do, you split them into randomly into maybe 10 different data sets, and you train them in parallel. Each one of these data sets will give you some function. And then that's like since they give you, each one is giving you some function, you have at the end, you have a distribution of the functions. That's how that you get this like XC, the context, they get mapped into the RCs, and then those are the representations. And then how they're getting mapped into those representations, they're just using the standard neural networks, like no crazy architecture, just mapping from one to another. And so that's going to be almost like our, from XC, when you saw the previous slide, goes into the encoder. The encoder part is the H in here that plays the role of that encoder. It takes the X, puts it in encoder, creates that Z function, and then goes to the decoder. And then here the decoder is the G. That now that we can, given that we have learned the Z, we can resample from it and learn the new labels for the data we haven't seen. I want to jump to
my understanding,
yeah.
With the Gaussian process, you typically have the idea that you have an infinite number of functions.
Correct. Yes.
For this, because I mean, of course, for any implementation, you actually can have an infinite number of functions. For this, like how many? I mean, you can have an infinite number of functions by having flexibility in your parameter space and having some combination of that. But for this, are you having distinct functions that you're having? For instance, like in a general additive model, you can have distinct basis functions. In this case, are you representing, like, do you have distinct neural networks that you're feeding into, or is it just basically all handled by one parameter space?
They are the same architecture of a neural network, but they all learn a different function. They approximate the data that they only see. So you're going to end up, if you parameterize it, I want my neural process to run with 10 parallel sets. So it's going to learn 10 different functions, 10 different approximations for the data. And those 10 different approximations.
You have to set it.
Go ahead.
You have to set the number of functions that you'll let it learn. It's like having an ensemble? Question mark?
Yes. Yeah. I mean, it depends how these guys implemented it, but this is how I'm imagining it. It's like, well, if you need to say like how many parallel sets you are doing, or maybe that's done automatically. You go from like as many as possible, and then you're training, and then you just keep shrinking them. I'm not sure how exactly they did it, but the gist is that it has to be in parallel for that to resemble that the Gaussian process. It's like, what are we taking from Gaussian processes? What we have to do, we have to learn distribution of the functions. And to learn the distribution of the functions, you have to make a data set, make sure a data set gives that ability. It gives you that 10 different, I think that what you go for the distinct, it's not entirely distinct because you don't feed it into different neural architectures. It's the same like ANN. The H is the same. It's just that the parameters, like the W's, or thetas, however you parameterize the neural network, those are going to be different. So the values are going to be different. Now, what R is here, the R means that he's going to, after you've trained all your representations, you're going to average them. And after you average them, now that's that you know something about the mean and variance, and that mean and variance is what powers up your Z, because now Z is some kind of like normal distribution, and you say like, well, I learned from all of my functions that on my average value is blah, and my variance is blah, and now I'm gonna instantiate that as a normal distribution. I'm gonna sample from there, and then go and then feed it into the decoder side.
So what does R means here actually? Is it like a function and then you get a mean and variance? What is R?
I would consider the H as a function. The R is a representation that you represented your input in whatever way. I don't know, like if say like if you have an image, maybe you represent that instead of pixels, like 100 by 100, you decide to represent it with like 2D data set. It's like anyhow that it's how do you want your neural network to learn the shape. No, I wouldn't say the shape of your data, but what is your neural network learning? Because now you have as many neural networks. Not stressing out not architectures, but as many neural networks, what they're learning something different. And then what they're learning is that the R is representation of your data.
Mm-hmm. So R is normally a function. So where do you get the mu and Z? Is it the weights of mu and Z?
You average the R.
Average the R, but R is a polynomial function. So what are you averaging there?
R is a polynomial function.
Yeah, finally, after you train the neural network, the output of that is a polynomial, is a multidimensional polynomial function. It's a big order. So eventually that's what it's going to represent. And how do you derive mu and Z from that?
I think it's just taking the parameters and then just averaging them. Taking the parameters that you learned.
I see. Okay.
Yeah.
As you probably have like a set of like n distinct parameters, hopefully like larger than 10, and then you just take the average of those. Probably with some sampling.
Okay. I see.
What happens in the function?
Sorry, what?
What happens in the function G? Yes, like the function G.
I couldn't hear really that. Did anybody hear the question?
Yeah, we cannot hear you.
We can't hear the question yet. Maybe you could type the question in the chat and somebody could read it.
I have a question as well.
The question of Joshua is what happens in the function G?
Is that question what happens in G?
Yep,
that's the inference happens in a G. That's like the reverse. It's I would say if I'm coming from graphical models, that's sampling. And then if you're coming from neural network, that's the decoder part. Does that answer the question?
Yeah. Yes, you said okay, got it.
Okay. All right. So to reiterate over here, somebody else asked a question?
Yeah. So you said that in the previous one, when we are actually averaging to get those, can you on the previous slide?
Yes.
On mu Z and sigma Z, we would be basically averaging the parameters. How are we sure that, like, if it's a polynomial function, it will have the same dimensions? and then we are averaging over it. If they have different dimensions, how would that work? Or we are restricting it to have the same dimensions?
What do you mean by different dimensions?
They're polynomial functions, right? I don't know how to.
Like they shouldn't have different dimensions if.
Yeah, it will be because x1, y1, and then move all the way to xc, yc. The output will be the same dimension.
Yes,
But
but I mean, even if you end up with a different architectures, let's say we go with a different architectures, and then if you end up with not something that you can average together, you can always do the padding. So make them to the same dimension, and then but there's like you have to be careful there because like if your Z starts to learn your paddings, it becomes a little bit more complex.
Yeah. Cool. Thank you.
Okay. Alrighty. So the bottleneck is that we tend to discuss this in detail is it replaces with a random variable. That's essentially the gist that you have to get from this what's a neural process that it replaces that Z with from the mapping to a random variable. And each pair that we talked about, the training data, the X and Y, is being represented with R, and then it passes through the basic ANN here. They didn't give an architecture with ANN, but I'm assuming just whatever I showed in one of the first slides, you have some basic layering. And the important thing is that you're training multiple data sets, which I already stressed out. So this one is a little bit like hairy. What happens here is because if you so far the previous points they were closer to the graphical models when you do like, well, how do you do the training, and then not how you do the training, how you present your variable with a random variable and then sampling inference, blah blah blah. With the neural networks, that in order to learn anything, you have to optimize. You have to have an objective function. What are you exactly doing? And the way I understand here, since we're coming from a graphical models, when you're learning in graphical models, that you have to optimize something which is called KL divergence, Kalbach-Leiber divergence, that looks at two distributions. Like what if I have here the P1, Pi1, and Pi2, red and blue, two distributions, the Kalbach-Leiber divergence would be like a green area. Will tell me what the difference between the distribution is. So as I'm learning in this neural process, I'm looking at the I'm looking at the target axis, and I'm looking at the Z. What is Z learning? And I'm optimizing over in that loop until these two distributions are somewhat similar. So that's what it's almost like reducing the error. So if you look at this gradient descent, it's looking at what's the difference between the Y label and Y training. You look at the error, and then you back propagate that error to do the learning. Whereas here you don't look at that Y anymore because you don't have it. As you're learning the function, you look at the target and you look at the context, and then it's almost coming from two directions, and then you start like learning and looking at the differences and what kind of distributions that they are producing until they start to coincide. It's like, okay, now I got the learning part. So that's what is the elbow method, the evidence lower bound. The nuance here is that, and that's like going into the weeds a little bit. So that Z variable, it's intractable, because especially if you have a large number of data points that you come in, you're never going to learn the exact function. So what people do is that they replace that with simpler approximate distribution. So here, that's why you would see the Q. The Q is the sort of like a lower bound function. So if, let's say, if I have, if my actual intractable distribution is some multivariate normal distribution of I'm trying to figure out how many dimensions that it has. It has like maybe 100 dimensions, and then you can't really learn that. So you're gonna approximate that with our simplest with a just normal distribution with the M and Z. That's not how they do it here, but in general, you're choosing a Q, which could be like the lower bound class. What is the dumbest thing that you can choose to be able to learn still something? So a lot of this, and this comes from the variational autoencoders, the way it's going from regular autoencoder to variational one, where you're trying to, your parameter, hyperparameter, is what kind of Q you're choosing, which, what simplification you're allowing into your system. And I hope I explained this right, because it's a little bit kind of too much into the weeds of what actually that one is happening. And then I definitely did not go into derive the math on what's happening here, but in general, trying to reuse what I know from graphical models to what they're trying to apply here, I understand where they're going with it. All right, and then so let's get to the interesting part. We're running out of time. So because that was like all the motivation for the neural networks, and then that was actually showing the neural networks themselves. So you recognize the architecture, and then it's super easy now to recognize, because you know why. You know how in math if you don't have to memorize the equation, you can rederive it. So same is here, it's almost like you derive from the simple one and you go to the next step, and next step, and next step. So it becomes straightforward. So yeah, what now? Like, why are we doing all of these different things? So that lines up very well with the zero-shot use case. So if you haven't observed any data, you have nothing, you can still use neural processes. And in how you use neural processes, if you have some prior. So if you put the prior on how that Z looks like, let's say as a user domain expert, you know something about your data. So if I'm responsible to be predicting the heights, maybe I know that my domain is the kids from the 7th grade. So I was like, well, I kind of know like what what's going to be the mean and a variance. So I put that as a prior, and without training any data, I can still make some predictions. And as I'm getting new observations, I start to learn a little bit more and start to tune it up and make it tighter and tighter. But I can certainly start with a zero shot. That's one beautiful thing. The second beautiful thing is that, well, that's just the next thing is like if you maybe have a few examples, few shot learning. So that is very similar to what the meta learning that they were discussing. That's the concept. So let's look at the one with the numbers, with the digits. So you have here number of context points. How many training examples have you seen? And it goes from 10, 100, 300, and 784. So what does that mean? So if you just have 10 points, and then you have the Z as your random variable. So if you have a Z as a random variable, you can sample from that. And if you sample from that, you can sort of predict what that digit is going to be. So if you only have 10 points, you one time you're running, one of the predictions says it's a 7. The second prediction says it's a 4. The next prediction says it's like a 3 or 5, because all of these 10 points are compatible with these 3 different digits. So it's not sure. It just gives you like, well, it could be that. It's almost like that's the point of running a variable. So it spits out something, like the closest thing that it can spit out. And then now if you're adding more context points, you have to go to 100 ones, that all 3 sampling return you a digit 3, because saying like now they see how the white points here in the context. You can already see that the 3 is there. So it doesn't need the entire image to be able to do the prediction of what that digit is going to be. And obviously, as you go more, you keep adding in more and more points. The sampling is just going to remain the same. So it's going to be, yeah, I know it's a 3. But you see how he was able to make a guess without having to finish seeing all the examples. So it can do it much faster. And the same with the faces. See how well, the face is a little bit more difficult with the digits, because with the digits you're gonna essentially say like it's one of the 10 the digits you all set. With the faces, it's like, well, it could be whatever, how many faces you have in your in your data set. So when you have only 15 points, all of these, the faces are like very different, and then you keep increasing, faces still very, they still haven't settled. And then only when you keep going more and more and more points, you can start seeing that the model is sampling the same image. Like only when you had like 1,024 pixels, you can see that all the faces, are the faces the same? They kind of look the same to me, yeah. That's a few shot learning. And is there something more? I think that what's more here is what these things are related to. Another beautiful thing about neural processes, they are kind of touched on a lot of different fields. They merge them, combine them. So the meta learning is where you have, you incrementally learn. How can I explain this better? So with meta learning, you might have seen a horse, but then you know something about zebras, but you haven't seen zebra. But if you know how the horse looks like, and then you have a description of how zebra is different from the horse, you'll be able to tell that that's a zebra if you see one. I hope that made sense. But it's almost like having some kind of rule about the unseen, but you have some concept of the class that you have learned. Now with the deep latent variable, that's from graphical models, where it's like pretty much where they shared architecture before, where you had the X flowing to Z, and then from there you infer the Y. Well, obviously Gaussian processes, that's exactly the way the inspiration was. Conditional neural processes, it's the same folks. First they came up with the conditional neural processes, and then they generalized to the just neural processes. Like it's the same thing. Well, it's the same thing. It's a general thing of that. And finally, Bayesian methods, because all of this reasoning and uncertainty and inference and sampling, that's all about this, what Bayesianism is for. So in the paper, they discussed similarities and differences with each of these different fields, which is really cool. And what's next after this? So they already have a new paper actually, which is called attentive neural processes. And then why did they have to come up with attentive neural processes? We couldn't just like finish on neural processes. So here's the why, what's the drawback. So with the neural processes, since it's the, it learns the distribution, distribution which fits your context and target, it underfits significantly. And then what that means is that if you have the points that you have seen before, your function is not guaranteed to go through that point. It's like, well, I'm learning my function and I'm just gonna ignore you that I've seen you before, but I'm not gonna use you into my context. So that's a neural process. And then same if you go to the face, you see that if before looking at the attention, even though it has seen the context, seen the eyes, when it did, and then but it haven't seen the rest of the face, it kind of smooths over the whole thing and ignores the fact that it already has seen the eyes. So it starts all over almost. It doesn't use the information that it had. So what attention, what they studied, they added a new thing is like, well, it's like we already have seen that, so might as well keep that information. So that's where the attention is. It's almost like context lays on top of the on your sampling, and it's like and it takes the priority. So same here with the curve. You see that now how it tries to force the curve to go through as many points as it can. Contrast that with the just simple neural processes where it's wider around the points. We are forcing it to fit. It's possible that this might be doing some overfitting. So I haven't read the paper, so I'll be very curious to see like what how they actually did that. I haven't read the paper. This is a new paper. Hopefully that next time we can read the attentive neural processes and then have more insight in how they did all of these things. But that's it. Thank you for listening, and I hope I wasn't too fast in. I tend to speak a little bit too fast, but we can ask questions now if you have more questions.
I just wanted to say thank you, Snejana. I think it was a very interesting presentation, very interesting paper. So thank you very much for that. As I was kind of at the beginning, I was kind of wondering, or this is also the question, the direction of my question. How would you say is it? How long do we really need until you can sort of, because this is actually kind of like a dream of mine, and I don't know if it's already there. How can we learn causal structures using, I know there's kind of hype around it, but essentially neural nets. So my idea is you essentially, we have giant data sets and sort of these structures, maybe the two algorithms combined that you just alluded to, sort of learn the causal structure by themselves and can even give us, causal insights.
So with the causal insights, I'm much easier to learn with the just graphical models. So
yes, okay.
Because there you put your domain. It's just like, well, I know how this data is supposed to look like. I'm gonna put that prior in, and I'm just gonna confirm what I know with the new data, or reject it if my priors have been completely off, and then my data is contradicting that. I'm learning also something. I'm learning something that my priors are not correct.
Yes,
so with the neural processes, I don't think that you can actually learn the causal structure. And then I don't think they're after that. They're not necessarily learning the causality. They're more learning, they're trying to fit the data points that they're seeing.
I see. So you would always need a domain expert to sort of hypothesize on the causal structure.
I think so. But again, maybe for somebody from neural network expert might tell me like, no, we can learn causal structures. It's just like I always say, like, I always love the graphical models because I can learn the structure, and then whereas neural network for me was always like a black box. It's not really doing this cool stuff. It just you plug data into it, and it eventually learns some kind of mapping, but there's no smartness into it. Versus with the graphical models, there's there's an interpretability, because now instead of just saying this is my box and these are my parameters, you're saying like, well, it's this one is distributed with normal distribution, this one is a Poisson distribution, this one is the other one. It tells you a lot about your data, and plus, if you're giving it the parameters, it also tells you something about the task itself. So if I'm predicting the heights of the people, again, the fact that my parameter is let's say 170 inches, and then if it has, if also the variance would tell me something about it. If I have a very large variance, which means that I'm looking at from anywhere from children to the very tall, like athletes or adults, right? So if a variance is large, but if a variance is tight, I'm also learning that my sample of the data is somewhat restricted to the specific area. Either it's like children in maybe certain group, or maybe a specific country. Everybody is super tall or super short. It tells me something about it. Versus neural network won't tell me that. You just predict me and then tell me like, well, here's what I got, and then you trust me. And then people don't like that trusting anymore. So like, don't trust me. It's like, tell me why. And this is why the uncertainty is something that tells you why. Because if you're giving the prediction of 170 inches, and you say like, well, answer is 170 inches, but I'm not really sure. And my margin of error is like plus minus 50 inches. That's huge, right?
Yeah, that's huge. That's huge.
Right. So, but the fact that if a model gives you that margin, you can make your own judgment as a human. How much do you trust it? It's like, well, you make a prediction, but the margin is huge. Versus with neural network, it will give you the margin, but you won't be able to tell, like, it will give you the prediction, the actual number, but won't tell you what the margin is. And then you are left with that blindly trusting that the answers hopefully are right, but that's not enough these days.
Yeah, true.
I have a question actually. So thanks for the presentation. This was very good. You explained a lot of details actually. It was a great presentation.
Thank you.
And question is the XT that we feed into Z to accommodate the new data, how do we, if we given like incorrect data, we will destroy our original learning. So is there a way to selectively prune the data that we give in addition to what it has learned already?
Pruning is that you give it more data, because
No.
you would hope that you're not going to have a lot of incorrect data, because if you have that model, because that's actually your model is dictating the constraints of how your data should look like, and then obviously you're going to have incorrect ones, but their probability should be small. The fact that, and then therefore they're not really messing up with the distribution itself. So when you sample from it, you're more likely to sample from the likelihood area versus with some versus in the tails. You know, like if you have a normal distribution, you sample a number. If you sample enough times, you're going to be somewhere in the center.
I see. So okay, so it is automatically taken as part of the Z learning itself, actually.
Yes, the fact that Z is a random variable and it's a probabilistic model, it does that. So that you have, again, in that uncertainty, again, is going to tell you like how much the data has shifted, either shifted your prior away, that you shifted your posterior away from the prior, and also tells you like how much data have you got. So if you start, it all depends on what kind of prior you start. At the beginning, if you don't have enough data, you hopefully gonna allow the prior to be as loose as possible. You're gonna say like, well, mean somewhere in the area here, but my variance is huge because I do not know anything. And then if you keep giving like few examples, that variance wouldn't change, because it's like, well, it's like I still do not know much. And the more data you give, the more that variance is shrinking and shrinking, because you keep getting more data, and that tells you how much have you learned, how much you have now added evidence to your model, not just using the prior, but adding more information.
Okay, great. Yeah, thanks. And do you also change the error measurement that you gave, the elbow thing? Do you also change that one?
What do you mean by changing? Like by choosing that Q?
Yeah.
Yes. So that Q is like that's probably the most complicated part of this type of inference, that you have to choose some way to model your Z with something which is more tractable. And then I think that's why you might do the experimentation, try different Z's, different Q's, and then see which one converges better. By converging, I mean if your KL divergence is smaller and smaller.
Okay, great. Okay, so one final question, actually, last question from me. So how does it compare to the complexity or the number of max or the number of resources needed, the neural process network compared to the standard neural networks? How much
that's an excellent question.
Have to pay the price?
I was going to say, I know how it compares to the Gaussian processes. It's the Gaussian processes is a cubic, and the neural net or neural processes is linear in terms of how many records you get. But how does that compare to the neural network? I think it's more computationally intensive, because with the fact that you're learning multiple functions versus just one, so it's going to be a little bit more. But it's not going to be anywhere near what the Gaussian processes are. Gaussian processes, the reason they're not being used is because they don't scale.
Okay. Okay. I see. Somewhere in between, I guess, actually.
Yeah, in between. But I think they're much closer to the neural network than they are closer to the Gaussian processes. So they're kind of using the Gaussian processes as inspiration, but they're still underneath. It's a neural networks. It's just you're doing multiple neural networks, and then you're averaging them and creating a random variable from there, and then do some sampling. So I think that process will take you longer to train, but the huge benefit is that you maybe don't need as much data as you think. And maybe that one shortens the training time, because like, well, you can start making predictions much earlier because you have some prior.
Okay, like we saw in the digits and images. Okay, great. Thank you. Thanks for your presentation.
Sure, that was fun.
Awesome. It looks like we maybe have one other question from Greg, and I could try to read it to you. It should be in the chat. He says, just wanted to double check how mu and sigma are calculated. Are the output vectors for each are aggregated to collect these samples sample statistics?
Yeah, so it's actually a question that it was kind of asked before, and then I think maybe I was too vague in there, and then that's part that I have to go and look back and what is exactly, how exactly it's computed. So I know that it's aggregated as like average, like mean of your parameters, but maybe there's more to that. So I don't want to lie and then give an incorrect answer. So I might double check the paper.
Okay, great. Yeah, then he continues, it also is each block of XC, YC disjoint from all of the other context blocks?
So that's a cool question. I don't think it has to be. That maybe in their set they chose them as disjoint, but I don't see the reason why it have to be disjoint. You can just like probably randomly sample like as in k-fold, like you just keep resampling your data like that many times.
Got it.
But it depends how they chose to do their training. I don't think they even mention if the data is disjoint. That's a good question.
Great. And then the last question is the assignment of the training observations to block fixed is the assignment of training observations to block fixed at the start of training, or do they get changed during training?
I think they're fixed. You start with like, you do a separation and you do a training.
Awesome. He says, thank you. Okay.
Thank you all for all these questions. That's awesome. I was hoping that it's going to be a lot of poking and then asking these important questions. It's super cool. And especially this is like for what I'm showing is that this is the paper for me, who is not an expert in neural networks, like by far. I was able to understand a lot from using the graphical model, the background from graphical models. So this is why I love the paper so much, and I recommend reading it because it's almost gonna cross the fields. If you know a whole bunch in one field, it's gonna click because a lot of things for me clicked as I was reading that. Oh, it was just exactly as an autoencoder. They're not mentioning that in the paper, but when I saw the graphical models, how they showed in pictures, like, well, that's exactly that. And the rest of the stuff was making sense. So how they do optimization, how they do the inference, how they do why it's underfeeding. A lot of things were making a lot of sense. So I hope I didn't offend anyone with the knowledge in neural networks by claiming that like I understood how that works. So
awesome.
Yeah. And I would love to do the next attentive neural processing, unless somebody else wants to take that, because we want to see like what's next.
Yeah, that would be wonderful. I was just about to say, so thank you so much for that presentation. It was really wonderful. I thought it was very clear and easy to understand. Great questions from everyone. I thought that was really wonderful. We had about 30 to 35 people in here. So yeah, really well attended. A couple of quick notes. One, I know that we started this and then I kind of fell off really quickly. My schedule got extremely busy with the semester, but we're hoping to do it every 30th or every end of the month, essentially. So the Sunday at the end of the month. If you're interested in presenting a paper, please shoot me a note on Slack, and I will get back to you and try to organize that. I would love to continue on with this kind of attentive neural processes. I think that would be really interesting as well. But thank you so much again. Yeah, really awesome, really wonderful presentation.
Thank you. And also, if people choose paper, that would be cool to be able to share the paper ahead of time, because I was trying to let people know so everybody has a chance to go through that, so we can have like this type of questions. So if you choose a paper and you know what you want to do, like just post it in Slack so we can all have a head start on reading it.
Awesome.
Alrighty.
Any other questions? Great. Thank you so much, everyone. Thank you for that presentation. That was really wonderful. And would you be willing to put the slides available online?
Yes, sure. I'll do that. Okay. Should I link them just in the Slack for general meetups?
Yeah, you can just post them in the Slack or shoot them to me, and I'll
awesome. I'll do so.
Awesome. Thank you so much.
Alrighty.
Thanks a lot.
You're welcome. Thank you for joining us. Thank you. Bye.